So we'll use this as our brief introduction into synthesis. So when evaluating a reaction, when you're looking at it, reactants and products, you need to be able to decide what things allowed that to happen. And that's what you'll encounter a lot of on, for instance, our tests, is you'll be giving a reactant and the product, and you're told what reagent should you pick, and you have to select a valid one. So when attempting to go through a problem like that, it might seem a bit forced in lecture, but in the real world, in a synthesis lab, it gets kind of close to that. You're given a final structure and you have to say, how did I make that? How could I make that? And you have to think backwards to come up with it. And that's the next step after synthesis. That's known as retrosynthesis. There, all you're given is a product and you have to think backwards. So synthesis works us up to that. So what you want to do is when you see any chemical reaction, you want to look at the reactants, you want to look at the products, you want to identify where the chemistry is in each of those structures, and then decide, did the chemistry move around? So for most of OChem2, you'll notice that our molecules are relatively simple and the chemistry is relatively contained. It's only really in one spot, and you just have to address how that one spot shifts or moves or changes. So one of the things that's important is to address this concept of chemistry. What is chemistry? So I did already address this in an earlier video, but that was a little while ago. So I'm going to address it again and hopefully use different words that maybe help make it resonate, no pun intended there, for you. So when we're looking at chemistry, it's really based off of two big aspects. It's looking at structural effects, which hopefully when you're looking at a synthesis question is straightforward because you're given the structure. And then you're given kind of secondary effects. This would be looking at things like electronegativity and everybody's favorite word, potentially resonance. Okay? And those two pieces kind of go hand in hand. Okay? Because resonance is going to be largely dictated based off of differences in electronegativity through the structure. Okay? So what you should be doing is look at the structure, now identify highly electronegative elements. Okay? And remember what we said, chi. So if we find a very electronegative element, say like an oxygen, we now know that it's going to start to move electrons towards it. Can it move those electrons via resonance? Okay, is resonance going to contribute to moving a pi bond, which is now going to change how our structure would look? For instance, if we looked at a carbonyl, what we should be seeing is that there is chemistry associated around that oxygen, or that oxygen's the center point on this. That chemistry is going to be, first and foremost, that it has lone pairs, but because it is electronegative, it could start to withdraw those electrons. Because those electrons are pi electrons, I could draw out a resonance structure, and this resonance structure goes and shows that there's a negative charge on that oxygen. Okay, a major way to highlight the effective reactivity there, and at the same time that those electrons shift up to the oxygen, I form a carbocation. So looking at a standard structure, what we want to be thinking towards is what is that resonance contributor? Okay, and that's going to help us predict chemistry. One of the things that can be tricky, though, is what happens, say, if we move to a structure that didn't have resonance. So in this case, we might say, well, that oxygen is, again, our electronegativity. We're really just looking at the lone pair electrons, and, well, that's it. That's all it can do. Well, no, the oxygen is electronegative, so it can withdraw electrons from that carbon. While it is not a resonance structure, so it is bad to call it resonance, we should be looking at that and realizing that that is a possible thing that could happen, which would mean I'd have that negative charge on the oxygen and a positive charge on that carbon. Okay? If I see those electrons as potentially doing that motion, I can now ask myself, is hydroxide stable? Okay? Or is that carbocation stable? Because if those things are stable, I've now predicted potential chemistry. I can now look to the other reagents and say, what are those reagents going to do to support the breaking of that sigma bond? Okay, so just because it's not resonance doesn't mean you should ignore it. There's a lot of negatives in there. You should be considering and thinking about that potential chemistry. Okay? After you've got the chemistry kind of nailed down, addressing, did the chemistry move? Okay, so if your alcohol started at a secondary carbon, so if we now change this out and look at an actual reaction, let's say we ended with this. Okay, did our chemistry move? Well, again, the chemistry is associated with that oxygen, but the secondary effects of the electronegativity, we're looking at the chemistry of how it's connected to the carbon has changed. Okay, instead of it being a secondary carbon, it's a primary carbon. So the chemistry has indeed moved. If we can acknowledge that, we get, number one, an idea of what reagents we might be needing to use if we can identify changes, and we can start to identify what types of reactions would be necessary to cause this to occur if the chemistry moved, which is why the next step of this question is which type of reaction completes that desired step. Okay? And again, we aren't looking at reagents yet. You're really just saying what reaction does that. So if I looked at that particular example that we've got drawn up there, okay, do any of these reaction types do that? Well, acid-base. Well, what is acid-base? What is substitution? What is elimination? What is addition? What is radical? Those were all things you learned in first semester. And you need to know at the back of your head so that when you look at this reaction, you can be like, well, damn, that's none of the above. Okay? And you might say, well, that sucks that it's none of the above. Welcome to OChem 2. It's not going to happen in one step. It's going to happen in multiple steps. If the chemistry has moved, then we likely have to string together multiple reactions. By deciding which reactions are going to string best, that's how we're going to start to decide what reagents we need to move through this. If you do it based solely off of reagent, you're going to be dead in the water because you don't know what reagents to put where because you don't know what they're causing to happen. And you end up just spiraling out into an infinite amount of possible solutions. And that's where it becomes problematic. Okay? So if you aren't familiar with the reactions, I highly recommend you look at this next slide that we're going to see here in a second, and you familiarize yourself with those reactions and their general structures so that you can recognize them. The next part, really zoom in and identify the elements or atoms that are missing from your desired reaction. Okay, so if we're looking at that in that previous case, we didn't really have any atoms missing, so we don't really get a big contributor here to help out. But if we went from an OH to a bromine, well, where the hell did the bromine come from? Well, that must have come from the reagent. So pulling out kind of the obvious things, letting them float to the top, and then try and work with those can really help you with a synthesis because it can simplify the amount of stuff you go through and do. After that, we get to the really advanced aspect. You have to consider the complications or the nuances of each of the reagents you've selected to use. So if you've decided to use a polar protic solvent, but stereochemistry is super relevant in your final product, that's probably not going to work because a polar protic solvent tends to suggest SN1, which means loss of stereochemistry. That's a lot of detail and nuance behind it. That's why OChem isn't a 2-semester class. It's a 1-year class, and you have to build on each of those pieces as you move forward. Okay? This takes practice. It's not critical to passing OChem 2, and I'm sure tons of organic chemists would yell at me for saying that, but I don't think it's critical for doing this. What I want you to get out of this is the practice in solving these things because it's going to help bring back reagents from OChem 1, it's going to help solidify reagents from OChem 1, and it's going to help you start to get used to the reagents that we're using in OChem 2 to help improve your knowledge and hopefully your exam scores. Those overall reactions, like I said, I promised would show up. We've got our acid-base. These are only the transfer of a hydrogen. Okay? Remember in my class, I reference acid-base only in the Bronsted-Lowry definition, so we're only talking about hydrogen only, or we're talking about hydrogen only, and more particularly a hydrogen cation. So the hydrogen ion, not hydride, different reaction. Okay? Substitution, it's the exchange or transfer of an atom. That's what acid-base is. But this time, not hydrogen. So anything that's not hydrogen that we've exchanged or transferred an atom, that's now a substitution. I don't know why my slide isn't advancing. That's kind of weird. We get our elimination, which is going to be the loss of 2 sigma bonds to form 1 pi bond. Addition, removal of 1 pi bond resulting in 2 sigma, so the opposite of the elimination. And then our radicals, which are usually just a giant mess of reactions, but there's really a small subset of kind of conditions that are going to force those, which really means if you're starting with an alkane, you've got a radical. Otherwise, try to avoid them if you can, but they will pop up every so often. Okay, but small amounts of radical reactions overall. That's a lot of text, and you're probably sick of text from reading the textbook. You're probably also sick of me already, but semester's young. Let's take a look at some pictures. We've got general pictures that are supposed to be representing each of these reaction types. You should be able to look at each of these and be like, yeah, I understand what those differences are, so that when you get to a synthesis question, you can be like, oh, that needs to do with substitution followed by an elimination. That needs to do an elimination followed by an addition followed by a substitution. Okay, recognizing those patterns can help you select and narrow down what reagents you have to use. So make sure you know these. How important is it to know these? I will explicitly test you on identifying what type of reaction you've got. Okay, so it's not just some one-off thing where I expect you to know it and then don't get tested. I'm actually going to test you to say which of these is a substitution reaction. So you're going to have to be able to look at it both from the mechanistic standpoint and from the overall reaction standpoint. The next thing that's kind of getting into here is what I'm calling here synthesis rules. These are just kind of rules for solving the synthesis activity that ideally would be done in groups, but I don't have a good way of doing that. Okay, so the synthesis activity has been posted to Canvas, synthesis activity, and it will show up in the Unit 1 information. Okay, and so it'll also show up with this rule set. So the goal is to use the structure cards, which we'll see here in a second, to help complete an individual synthesis that you're being asked to solve for. Okay, and so the best synthesis is to use the minimum amount of correct structure cards. As you do that, you also want to be able to say what reagents cause that transformation. Okay, this says the sets are color matched. I went through and did a bunch of editing, didn't fix that. They aren't color matched for you because they're not printed out for you. It's in a document that you have to print out if you were going to do it that way. Okay, but you get set 1, set 2, set 3, so 3 different sets. Higher numbered sets require the use of their cards, but can also use set earlier cards. So a set 3 synthesis can use set 3 cards, set 2 cards, or set 1 cards. Okay, any of the above. But set 1 cards or set 1 syntheses can only use set 1 reagents or cards. Okay, all reactions will require the minimum of 1 new structure. Okay, which means there's 2 reactions. But you can use multiple structures in multiple different places. So don't start eliminating cards because you're like, oh, I used that one already. You can use it an infinite amount of times. Not infinite. Okay, so this is roughly an example of what it looks like. The very first page has what's shown in the upper left-hand corner there, which is this kind of grid pattern. And you'll notice A, B, C, okay, the letters listed out there, and then a 1, okay, for each of those. That 1 is because these belong to the set 1, okay? If we look down at the very bottom set down there, we see A2. So A, B, C, again, labeling out the cards so you could then reference these, okay, but those are now set 2 cards, and there's the set 2. Okay, I didn't show the full page here, but that's the rough breakdown. These are your structure cards. The structure cards are what you're supposed to use to help you move through a synthesis. So if we were to then decide, well, what's a synthesis? That's what we're saying in the lower right-hand corner. These would be your set 1 syntheses. So what you're expected to kind of do, and if we met in person, I would have already done most of this, okay, is you would print out all the structure cards, you'd cut out each of the cards, and then you'd go to these syntheses and you would find the cards that matched. Okay, so as a general kind of rough walkthrough on this, let's see if I can do this right. If we were to pick this first synthesis, well, what I want to do is find first this card. So I go up, because I'm in set 1, I don't need to look at any of those. Okay, and it is right here. So I could say I1 does something. I know minimally I have one card here, so we could start with this. Goes to then this guy, which is H1. Okay, so I want to know what card should be placed in here. Okay, and this goes back to what we talked about. What's the chemistry that we can identify in this particular reaction? So if we went to go through and look at this, the chemistry is this pi bond, chemistry is this pi bond. Did it move? Yes. Okay, and in particular, if we're going to really drill down on this, the chemistry is at this carbon and this carbon, whereas in the other one, it's at this carbon and this carbon. So really, the chemistry moved from being here to out there. So we definitely have the chemistry changing positions. Okay? Do I have any reaction that allows me to just shift a pi bond at once? Well, no. The only thing that could involve a pi bond would be an addition reaction, okay, which would be the loss of a pi bond. But I still have a pi bond at the end. Okay? So at the very beginning, I know I need to do a loss of a pi, but then I also need to gain a pi. Interestingly enough, the loss of the pi would be an example of an addition reaction. The gain of the pi would be an example of an elimination. So right away, I could start to guess that that first step is going to be an addition, and the next step is going to be an elimination. To do that addition, I would need to add two pieces. Okay, what two pieces could I go through and add to that? Well, let's look at the chemistry. In the process of losing, let's clean some of that up, losing chemistry at that carbon, what happened to it in the product? Well, that same carbon at the other side is just gained a hydrogen. Okay, well, where did that hydrogen come from? That had to have come from the addition, which means H needs to be supplied in this reaction. Okay, if I were to look at resonance of that pi bond, I would predict that those electrons would go outwards, because that would be putting a carbocation in the tertiary position, which is the more stable position. So that makes sense, which means the H that I would need to place there isn't just an H, and of course my computer doesn't want to work with me right now, would be H+. Well, what has to go then to the other position? Okay, I can't simultaneously remove that hydrogen to make the new pi bond. That's just not allowed. Okay, none of my reaction types allow that. So I'm going to have to add something. That's something that I add now to this position. I want to be able to remove, because when we look at the end, it's not there. So if I'm going to put something on and then later take it off, well, it needs to be able to leave the structure. So it should be a good leaving group. Halogens are good leaving groups. I could put in something like Br-. So if I added HBr to this, where would that place the H? Where would that place the bromine? Does that match the pattern that I want it to do? Okay, that seems reasonable, which means as a reasonable guess in between, I'm now starting with something connected here and an H connected here. So now I could go back to all of my pieces and see, well, G doesn't work. Okay, the rest of them aren't obvious. G didn't work because we had that double bond. I don't want a double bond. I want an H at that position, so this is okay. This isn't. This is okay. This is okay. This isn't. And this is okay. Okay? So what we're trying to do is identify that I just have those pieces present. Of those, which of them also now match that I have some kind of leaving group there? Okay? Well, D1 is now looking pretty phenomenal. Okay? F is putting an H where I want it to be. Okay, where I want that leaving group to be. So that doesn't make sense. CI doesn't work. C1, sorry. B we already get rid of. And A1 could work too. Well, you get OH. Okay, but remember, I want a good leaving group as well. Which leaving group is better? OH minus or BR minus? I like BR minus better, so I'm probably going to pick D1 to be that species. I now have a potential synthesis, and I've already started to work through some of the reagents. Well, what about the next step? The next step is an elimination. How do I force the elimination to occur? Okay, well, a strong base would be a phenomenal idea. I like that idea. So let's pick something like hydroxide. Okay, where does that take me? Does that take me to the final product that I want, or does that take me somewhere else? That's the process you're supposed to be thinking of and moving through. And that question is a very important question to answer. And if you can't answer that, you should talk to me because that's why I'm here. Okay. With that, thanks for listening for our general synthesis activity or our intro into it. Good luck with it. Let me know if you've got questions. Hopefully this will help you through with it.